Hi everyone, let's get started. The topic of this presentation is an evolving neo-fuzzy system with adaptive learning for online forecasting of non-stationary processes. Mathematical forecasting of time series data is well studied with many theoretical and practical approaches. The challenge increases when sequences have unknown non-stationarity trends. Existing narrow fuzzy systems struggle with real-time forecasting and a significant non-stationarity. The neo-fuzzy approach enhances forecasting by dynamically adapting to changes. However, it has traditionally been assumed that the sequence varies with a predefined range. This work proposes an evolutionary neo-fuzzy system for forecasting highly non-stationary sequences in an online mode without predefined range constraints. As the basic architecture of the nonlinear predictor, it's quite convenient to use the so-called Anarsk model, which has the form of equation 1. The convenience of model lies in the fact that the general task of constructing a nonlinear adaptive predictor is decomposed into an subtask of synthesizing two input models, where the input signals are y of k minus l and x k minus l, while the local predictor fxl can be adjusted independently of one another. Figure presents the scheme of a neo-fuzzy system designed for real prediction of non-stationary processes. The first layer of the system consists of two delay elements, the inverse, which forms the historical context of the predicted process, yk minus l and xk minus l. The second hidden layer consists of n neo-fuzzy element, nfexl, and forms the component of the forecast fxl, where l is in range 1 to n. Finally, the output layer consists of a single summator where the final prediction is computed. The key element of the system are the nonlinear synapses, which directly solve the problem of approximating the historical data of analyzed sequence. Figure shows the structure of neo-fuzzy element NFEXL, which consists of two nonlinear synapses. Each of the nonlinear synapses contains h membership functions and h adjustable synaptic weights, which must be continuously updated during the processing of the predicted signal. So, upon receiving the input values y k minus l, x k minus l, the output of NFEXL forms the value given by equation 1, which is a component of the required forecast 2. Once the membership function system has been formed, it is possible to proceed with adjusting the synaptic weights of the system. Suppose that by the keyed moment in time, the prehistory vector of the analyzed sequence and the values of its membership function are formed as equation 1. Next, using equation 2, we defined vector of synaptic weights with the same dimension. Then the forecast of sequence at moment key can be written as 3. After the actual value y of key is received by the system, the synaptic weight vector can be refined using the adaptive learning algorithm 4. Triangular functions are typically used as a membership function in neo-fuzzy neurons as they satisfy the condition of unity partitioning. The advantage of triangular function is that at each training step key, only two neighboring membership functions are activated, meaning that only for n synaptic weight require adjustment, which simplifies the learning process. In our opinion, Yapaneknikov kernels, which have proven to be highly effective in regression and pattern recognition tasks, can be more accurate, can give more accurate result in compared to triangular functions. To construct the system, it is necessary to define the range of the control sequence and the number of these functions, which is usually chosen based on purely empirical consideration. The distance between the extrema of two neighboring functions is determined as shown in equation 1. The functions themselves can be expressed as equation 2. While forecasting non-stationary sequences, unexpected spikes and rapidly rising or falling trends that exceed the expected range may appear. We believe that this problem can be addressed by leveraging ideas from evolutionary system where not only synaptic weights but also the system's architecture are adjusted during the learning process. Reconfiguring the architecture in real time is quite challenging. Therefore, it's advisable to limit modification to the evolution of the membership function system while preserving their number and the number of synaptic weights. Suppose that at a certain moment in time, the predicted sequence takes a new value greater than Cxh, as shown in figure. Based on the value, a new membership function is formed with the center of this new value, and the previous functions become asymmetric. The membership function with center as x1 will be removed. To perform experimental verification and compare the obtained result, we constructed an evolving neo-fuzzy system with triangular membership and panechnical functions. As test data, synthetic time series generated using Formula 1, where y of t represents the function values at time t, sinus of t is the primary sinusoidal signal, and sigma is the noise level, which determines the intensity of Gaussian noise in the data. Exc of t follows a standard normal distribution. 3 variations of time series were considered: a clean sinusoidal signal without noise, a signal with low noise, and a signal with higher noise. The main criterion for evaluating forecast accuracy was the mean relative error. Initially, forecasting was performed using two kernel membership functions defined over the initial range of time series values from minus 1.5 to 1.5. As seen in figures, both methods demonstrated high accuracy for a pure sinusoidal signal. However, in the presence of noise, the functions proved to be less resistant to fluctuation, leading to an increase in error. But in all cases, the model using a panechnical kernels showed slightly less error than the one using triangular functions. At the next stage, to verify the evolutionary component of the method, the initial interval was reduced, allowing for the simulation of the case where the observed values exceeded the predefined range. As shown in the figures, the forecasting accuracy slightly dropped by around 1% compared to the previous experiment. However, the model utilizing a panechnical kernels still proved to be more effective. So the proposed evolutionary neo-fuzzy system is designed for forecasting significantly non-stationary stochastic and chaotic sequences. The conducted experimental verification has demonstrated the effectiveness of the developed system. Thank you for your attention. We are open to the question.